everything set up, and then I got some news. So anyway, we're in 8.6, so let me get that started. And I wish I had done this part, but the news I got interrupted me before I got this done. Okay. And let's see. I'm going to also set up the whiteboard, even though I'm not going to use it right off the top. So sorry, I'm, like I said, running a little late. And when I tell you the news, you'll, I think, understand a little bit why I'm a little disjointed. So anyway, all right, let's go back to the PowerPoint. 8.6. Okay. And we'll go from current slide. Okay, this is where we'll begin, but let me go and give you the news now. It's not anything you can do. It won't change anything, but just to let you know, I haven't been faking it the last little bit of time. I went in this morning for blood work. There's my band. Okay, because I was supposed to have an infusion Friday. And normally they do the blood work right before the infusion and go on and set you up and get ready to give it to you. I didn't want that to happen because I figured like I've been telling y'all, I think, I assume I've told this class too, felt like I was really anemic, and that I knew they were scheduled me an appointment, but I didn't think I'd need it. But I didn't want to wait until Friday morning and then they couldn't get in touch with the doctor and say, well, let's go on and give it to them anyway. So I sent a message on Sunday night to see if I could get the blood work done this morning on Wednesday, and that way they'd see it before I went into for the treatment. So I finally got an answer back late yesterday. They didn't respond Monday. They finally responded late yesterday and said, yeah, it's set up, get it, anytime tomorrow that you want to. So I went in early this morning and had the, yes, you have a question?
Emily was telling me because I left my computer for a
Okay.
second.
So I went in this morning for the blood work, and then I came home. I didn't realize she had tried to call. The nurse had tried to call. And I just got called back when I saw that there was I was going to use my phone for computer, calculator, and I saw I missed a message, so I called back. It was on hold and all this kind of stuff. They tried to get in touch with the person, and when finally they did, all that they said was, had a tremendous response to the Godiva, that was a drug last month. I could have told them that on Thursday. They gave me a 10% dose on Thursday and the 90% on Friday. I could have told them after Thursday it had wiped out everything. I could just sense, I could feel it was at work. I was hot. I was eating ice, anything to calm it down. And then I had the 90% dose on Friday, and I hardly felt anything then, a little bit, all the, just little things. But I could just tell it was just mopping up whatever was left. So anyway, right before the treatment, I was feeling really exhausted. And then certainly right after the treatment, I could hardly do any. When I walked upstairs, I was just breathing hard. When I laid down to sleep, I could hear my pulse beating, and I don't usually hear that, so I knew I was anemic, really anemic, and my heart was having to really work at getting enough oxygen to everything. And it's been getting better ever since, but awfully slowly. So when she called today, she said, you had a tremendous response to the Gazyba. I could have told her that after the 10% dose. And she said my counts were like 1.7, and they're supposed to be between 4,000. That is 1.7 thousand. They're supposed to be between 4,000 and 11,000. So, and this is a month ago. So, but then she said you're extremely anemic. Platelets are almost dangerously low. My neutrophils are basically dangerously low. Everything is dangerously low. Hematocrits, everything. I need a blood transfusion. So I could have told them that, almost. I didn't think it was that serious. But anyway, I've got to leave this afternoon right at 4 o'clock. I won't be able to be here for office hours today. I don't have any appointments scheduled. Just checked that this morning, and go get typed and whatever they call it for a blood transfusion. I'm going to get that on Friday. I hope maybe we can talk them out of that, but we'll see. So when after I got off the phone with her, I called my wife to let her know. She had already gone into work, and she said, "Wow." And so anyway, that's where things are sitting now. So all this stuff about my being tired and just running no energy, and now I can confirm it. It was truly true. I knew something was wrong, but I didn't know it was this serious. So anyway, we'll go on and have class. The nurse said I shouldn't be working today, but all I'm doing is sitting here talking, so it's not anything I haven't done, and I felt far worse right after the treatment than I feel now. So anyway, we'll go on and proceed with class. But just to let you know, I won't be in the office this afternoon. That was too long a story for all that. My wife says I give way too many details. So anyway, that's there. All right, here we go. Any questions from you? Any comments? I do want to say this. Are any of you, I think all of you are returning in the spring, right?
Yes, sir.
Okay. Have you already registered for spring?
Not yet.
Not yet. Did you know? Okay. Did you know that today and tomorrow they're doing advising and registration on campus, both campuses, Birmingham and Bessemer, from 9 in the morning until 7 in the evening? And there have not been big crowds yet. I talked with my boss this morning when I was waiting to get the blood work done, and he I had hoped to be back home before 8, but my wife was parked behind me and she wasn't ready to leave when I was ready to leave. So anyway, I was running a little later than I intended to, so I called them to let them know that, and to let them know I was going to have a treatment on Friday. I thought I was going to have a treatment on Friday. I was hoping I wouldn't have a treatment on Friday, which I'm not, but I didn't plan for a blood transfusion. So anyway, um, uh, well, I called my boss and I asked him how things were going with that, because I can't go to campus and do it. And he said it's been awfully slow. So if you want to go to campus, okay, my advice to you would be go to the um, virtual advising center, sign up, get advised there. Okay, and as soon as you get advised, then enter the courses that you need to take for the spring. That would be the safest way. That would be the best way to do it. However, if you want the one-on-one, if you have questions that you don't think you can get through the virtual advising center, or that you're not sure you can get the system to work the way you want to, they're going to be there. They're going to be there on the Birmingham campus, and that new Academic Success Center where Winona Elementary School used to be. It faces Wilson Road, but you can't enter it from Wilson Road. You have to enter it at the light, drive around, and park in the back of that building. I don't know how the crowds have been there this week. He had only been at the Bessemer campus. He said the crowds are not crowds at all, but he said maybe 30 students on Monday and maybe 40 on Tuesday. He was just estimating. He said it's been pretty slim, and there they had all the faculty members on campus signed up for multiple hours and stuff. It just was ridiculous. But anyway, you can do that on the Bessemer campus. It's in the Ethel Hall building. Now, that's not the Ethel Hall Nursing Building on Birmingham East Campus. It's on the Bessemer campus. It's the newest building on the Bessemer campus. It's the one fairly close to the Bessemer Civic Center on the south side of the campus. And there's a big parking lot when you go in that gate near that. And then you walk up around the building and come in what is the front of the building, but it's not the back of the building is facing the parking lot. So come in the front of the building, and the Ethel Hall Auditorium is right there. It's not much of an auditorium. It has a stage, and that's about it. Big open room, that's all it is. So you can get advising and registration done there. All right, any questions?
When does registration close?
It doesn't close. They're just trying to get the numbers up. They'll still be registering. They want everybody registered as soon as possible, but they'll still be registering up until I can't remember if it's a week before classes start. It's about 2 days before classes start. They'll be doing general registration usually 2 days before classes start, and then you still have drop add period for a week after classes start. So, but the thing they want is as many people registered as possible, because you see, once you get close to the classes starting, they start canceling classes. And if they don't have enough students in a class, they're going to cancel it. And then if you go and try to register during drop add, there's no class to register for. So it's to your advantage and the school's advantage that you register just as soon as you can. But yeah, you can register right up until the day before classes start. But they will be canceling classes earlier than that. So get it done as soon as you can. Did that answer your question adequately?
Yes, sir. Thank you.
All right, good deal. Good question, too. All right, any others? Okay. And I'm wondering, when I look at myself in the camera here, I think I look fairly pale, okay? And I noticed in Sunday school class, one of the members of the class said, "Are you anemic?" So I thought she had just heard that because I'm not shy at telling people that. But now I'm beginning to think I must really look bad so if she said that. But anyway, I don't know if y'all had thought that as well. But anyway, let's go on and hit example 2. Now, example 2 is here on the PowerPoint. It's also at larsoncalculus.com, and you can see an interactive version of this type of an example. So it says use Simpson's rule to approximate that same integral we did before using trapezoid rule, the integral from 0 to pi of sine x dx. And we already know what the answer is because we did it last time. I'm going to write it down for you here. That answer is 2. Okay, that is the integral from 0 to pi, and let's see, it's back at example 1. At the end of example 1, it gave you exactly that. Now, and it says compare the results for n equal 4 and n equal 8. Now, that's exactly what we did in example 1, and I'm going to write down those answers before. In the trapezoid rule, for n equal 4, we got 1.986. I'm sorry, I said it back at 1.896. Pretty close to 2 with only an n of 4. When we up the n to 8, we got to 1.974. That is really good. Okay? Now, we're going to do it using Simpson's rule. Now, just as a review, and I can't remember if all of you were here last time, but just as a review, here's Simpson's rule. Now, the function has to be continuous from, we're using a to b is 0 to pi. We certainly are, sine function is continuous everywhere. Okay, so that's fit. Let n be an even integer. We're going to do 4 and then 8. Both of those are even integers. Simpson's rule for approximating that integral, the integral from 0 to pi of sine x dx will be this, okay? b minus a, that's pi minus 0 over 3 times n. Now our first n is 4, so that's going to be 12. And then we're going to proceed with these values here, okay? So we're going to do a f of 0, and by the way, that's for us will be 0. X of 1 will be pi fourths, pi fourths, then pi halves, then pi 3/4 pi, and then our last one will be pi, okay? Those are the 4 divisions, okay? That's the minimum, well, not quite the minimum, but yeah, just about, okay? So let's get that down. Remember, your coefficients here are 1, 4, 2, 4, 1, okay? Coefficients 1, 4, 2, 4, 1. Now when we go to 8, we'll have some more 2 4s, 2 4s, 2 4s in there. But that's what we're doing. So it's b minus a over 3n, and then times this, okay? So let's do it to it, okay? What we'll need to know is sine at 0, that's the first one, and we know what that is. That's 0. Sine of, when n is equal to 4, it'll be pi divided by, pi minus 0, pi divided by 4. That's pi fourths. We know what that one is, okay? And then we'll have sine of pi halves, and we'll have sine of 3/4 pi, and then we'll have sine of pi. Now, that looks like 5 places, but you got a beginning and an end with 3 in between. So it's 4 subdivisions, but you've got an end on each side. Okay, we know what this is. Sine of 0 is 0. Sine of pi fourths is root 2 over 2. Sine of pi halves is 1. Sine of 3/4 pi is also root 2 over 2, and sine of pi is 0. Okay, do I remember those? Yeah, but we did them last time, so there they are. Okay, so what was this integral according to Simpson's rule? Okay, let's go back and review. b minus a, that's pi. b minus a divided by, whoops, wrong way, 3 times n. Our n is 4, okay? So that's going to be 12, okay? Now, that's multiplied by 1 times 0. That's just going to be 0. Plus, and the next one, remember, was 4 times f of x1. Okay, so that's 4 times root 2 over 2. Okay, plus 2 times 1 plus 4 times, that's ugly, okay, root 2 over 2 plus the last one is just 0, okay? Now, this will go into that twice. This will go into that twice. You have a 2 in every factor here. There's a 2, there's a 2, and there's a 2. So 2 will go into that 6 times. So you have pi 6 times root 2 plus 1 plus root 2. Okay, so that will be pi 6 times 1 plus 2 root 2. Okay, I'm going to pull up my handy dandy calculator again, hoping I don't have another message like I did last time. Whoops. Okay. And let me turn it sideways to get the scientific calculator mode on. Pi divided by 6 times, open parentheses, 1 plus 2 times, I have to do the 2 first, then do the square root, then close the parentheses, and equal. Something didn't work right. Let me try that again. Okay, let me clear that out of the way. Okay, pi divided by 6, pi divided by 6 times, open parentheses, 1 plus 2, I forgot to put the times sign, 2 square root of 2, close parentheses, equal. Look at our answer. 2.0045 blah 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 blah. Okay, so on a good day, Simpson's rule, there was trapezoid rule, Simpson's rule for n equal 4 is already much better than trapezoid rule was with n equal 8. This is 2.00456. Okay, wow. To 3 significant digits, you have it right on the money, 2. Okay, can we get any better with 8? I bet we can. So I'm going to, I should have done something else first, but that's okay. I'm going to plug in my calculator again while I'm doing, because I was using it a lot this morning. Need to get the charge back up. Okay, so there's n equal 4. Let's do n equal 8. Okay, now I'm going to save as much as I can. Okay, so let me erase what I can. Okay, I could have left that. Let's erase all that. Okay. Okay. Because I will need the room. But I wanted to leave some stuff just to keep from having to write it again. Okay. Let me go back and pick up my pen again. Now, the reason I left this is that we now are going to have an n equal 8. So that means rather than just 4 entries plus 1, we're going to have 8 entries plus 1. And they're going to be right in between this. So the next one is going to be the sine of pi eighths. Okay, and we'll fill that in just a minute. Then we'll have the sine of 3/8 pi. We'll fill that in a minute. And then we'll have the sine of 5/8 pi. And then finally we'll have the sine of 7/8 pi. I don't have room to write it, so just if you want to know that it's here, I'm just going to put 7 pi over 8. It should have a sign in front of it. I'll try to write it in. Okay, there it is. Now, before you get to pi. Okay, now, if you remember from before, sine of pi eighths is the same as sine of 7/8 pi. And sine of 3/8 pi is the same as sine of 5/8 pi. So I'm just going to write those numbers down twice because I don't have room to fill in the blanks, and they're not quite as easy as this. So let me get my calculator back out and clear that. Turn it sideways here to get the scientific calculator mode. And what I want to be in radian mode, and I am, you can see that because there's the RAD, and this is how I changed back to degree, but I'm in radian mode now. That's where I want to be. I think it's left over from Monday. So let's do pi, and I have to do it this way, divided by 8. I have big fat fingers and little bitty keys here, equal, and then I'm going to take the sine of that. And the sine of that is 0.3826834, blah, 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 blah. Okay, I'm just going to write down a number here. If I could get my pen to show up. There it is. Okay, that sine of pi 8 is 0.3. What am I talking about? 0.3826. I don't know how many I want to put there. 834. I'm going to quit. That's going to be, may not be enough precision. Now that's going to be the same as sine of 7/8 pi. So the only other we need to do is sine of 3/8 pi. That's going to be the same as sine of 5/8 pi. So let's do that. 3 times pi divided by, no, it still didn't, divided by thing doesn't pick up well. Okay, divided by 8 equal, okay, and then take the, we're in radian mode, take the sine of that, and that gives me 0.92 blah 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 blah. So let me write this one in here, 0.923. That is a 2. I don't know why it came out looking like a 3. 92388. Okay, that will be close enough. It goes on forever. Okay, now wound up with 5 digits in both of them. That's fine. Okay, so I think I'm through with the calculator for a moment, so I'm just going to let it sit. I'll plug it back in so it will be charging while it sits. All right. So, what is Simpson's rule for n equal 8? That will be, if you remember, b minus a, which is our pi, divided by 3 times n. That's 24 for this one. Okay, times f of 0 is 0. Okay, now 4 times this one. Okay, so it's going to be plus 4 times 0.38268. Okay, plus 2 times this one, root 2 over 2. Okay, plus 4 times, let me make sure I haven't missed one. There's 1, 4, 1, 4. Okay, so that's that one. Plus 4 times 0.92388 plus 2 times 1. That was the sine pi halves. Now, it's going to be 4 times this one again. Okay? Well, we already have this one. Remember, that's the same. These two are the same. So let's just make this an 8 here. Okay? I'm trying to get my pen to cooperate. It's trying to, but okay. Let's make this an 8 here. Oh no. Yuck. Okay. Goodness, this pen is nuts. 8. There was a plus on there. That was a root 2 over 2. And that was a 2 times that. A plus there. And a parentheses there. I think I got everything back. Okay. So now we're up to, we've taken care of all the ones up to here. And now we're going to have a 2 times this. Well, we already have a 2 times that. So let's see if I can get the eraser to be a little kinder this time. And we'll make this a 4 here. Okay. 4 times root 2 over 2. And then, so that takes care of that one. This one, the one that we snuck in there, that's the same value as this one. So we'll make this an 8. Okay. Let's see if I can get the eraser to be kind again. Okay, that time it was a little better. And that will be an 8. And then you finally have plus sign of 0, which is 0. I mean sign of pi, which is 0. So I'm not even going to write the 0 in there. Okay, we'll forget about this one too. All right, now we'll pull out my handy dandy little calculator that I left the 0.92 thing on. So since I left it on there, I'm going to go on and multiply that by 8. This times 8 plus, now I've just got to keep up with the other things, another 8 times 0.38, if I can read my writing, 268, okay, plus, okay, and I should have done this wherever I put my pen. Go on and cancel the 2 into 4 and make that a 2. So that's going to be plus 2 times root 2. I have to turn my calculator sideways to get the root 2 to work. Okay. And then I think all we've got left is a plus 2. Okay. I got 15 point something another. Let's see if it's right. Multiply that times pi and divide that by 24. And here's what we get. 2.002. Yes, we improved it. You know, couldn't go much better, but we did get better. So for n equal 8, this is getting really messy, isn't it? And I think, oh, here it is. Simpson's rule for n equal 8 is 2.0002655. Okay, I've got to take care of something for just a minute. Hold on just a moment. Howdy, thank you. Okay, I didn't need to take care of it. She took care of it for me. Every other Wednesday is the cleaning lady day, and she just came in, so I had my door open in case I needed to hear the phone ring or anything. So she just came up and closed it. So anyway, that's taken care of. So I stopped at 2.26, and I could go on and on and on. It probably should be a 2.7 there. I'll stop there. If I could get my pad back. Okay. This is, where are you, pen? There you are. 2.7. Not that it makes much difference. Wow. 1, 2, 3, 4, even 5 significant digits, that rounds to 2. That's pretty good. So Simpson's rule with only 8. Now notice up here for trapezoid rule, you're off by more than, oh goodness gracious, I got another phone call coming in. Because this could be important, I'm going to pause the recording and answer the phone. Sorry about this, probably didn't care about hearing that. Okay, any questions on this example we just finished. And we did finish it. And let's just see how they did in the book. They said at the n equal 4, they rounded it to 2.005. They used the 5 to round the 4 up. And for the n equal 8, they used the 6 to round up to 2 to a 3, 2.0003. That's awfully close to 2. So you see, numerical integration can be done pretty reasonably. And you do this with a computer, not with a calculator, it'd have been done like that. And usually on that you designate what kind of precision you're interested in. Most of the time, if you're within 3 significant digits of what you expect, you're happy. And this would have gotten us, the trapezoid rule would have taken us probably another maybe 16, n equals 16. I don't think it would have taken us up to 32. But you see, computers can do it really, really quickly, because just like we saw, we had half of the values already calculated. When we went again, all we'd have to do would be pi 16ths, 3/16 pi. We just plugged in a few more and then put it back into the system. Computer can do that so easily. Okay, but with the Simpson's rule, we were already there. If you had 3 significant digits, this would have been there, right there, and you probably would have stopped at 4. If you wanted more precision than that, I can't imagine you would have wanted anything more than n equal 8 would have given you. So it's a pretty quick process. Okay, any questions on trapezoid rule or Simpson's rule? All right, let's see how they did it. Let me clear, if I can find my screen. This is sort of, there it is. Okay, there it's coming back. Erase all the ink here so we can see how they did it. When n is equal to 4, your Simpson's rule here says pi over 3 times 4, that's 12, times sine of 0, which we know to be 0, plus 4 times sine of pi fourths, which we know to be 2√2, plus 2 times sine of pi halves, which is just 2, plus 4 times sine of 3/4 pi, which is the same as this, again, 2√2, plus 0 again. Okay, so that came up. They didn't show you the details. They just said that came up, rounded to be 2.005. It actually was better than that, but they just rounded to 4 digits. Okay, when n is equal to 8, they didn't show any of the details. They just said you get to 2.0003, and it's even better than that. Okay, so again, really, really great convergence there in very short time. Okay, any questions there? All right, the next thing we're going to do is error analysis. This is the top of page 563. Okay, and when you use an approximation technique, it's important to know how accurate you can expect the approximation to be. The following theorem gives the formulas for estimating the errors involved in the use of Simpson's rule and the trapezoid rule. So here they are, the errors, and here I am yawning again. And I'll say it honestly this time, I'm anemic. I'm really anemic, so I didn't bring up a Coke either, so I've been living on caffeine and sugar, so I may run down and get one in a bit, but I think I can make it through this class. How we're doing? Yeah, we have less than 50 minutes to go. Okay, think I can manage. Okay, here's the theorem. Errors for the trapezoid rule and Simpson's rule. If f has a continuous second derivative on the interval a to b, and the ones we were doing, sine, has as many derivatives as you need. Most functions will have, potentially have continuous second derivatives. Then the error e in approximating that integral by the trapezoid rule. that error, the absolute value of the error, because the error could be plus or minus, so they just do absolute value, will be less than b minus a, we were using pi here, cubed. Now that makes a pretty big difference there, because whatever your interval, and the longer the interval and then you cube it, that could increase your error pretty significantly. But then you're dividing this for the trapezoid rule by 12n squared. So the more intervals you have, then this goes up really big time. We went from 4, which would have been a 12 times 16 down here, to n equal 8, which would have been 64 times 12. That's a big, big denominator, and the bigger the denominator, the smaller the error. And then here's where you need that second derivative. The maximum second derivative, absolute value wise, on that interval, okay, from A to B, that that you're measuring to. That's where the second derivative comes into play. So this is a generous error adjustment or analysis, because that's going to give you the biggest second derivative you have. And if that's a huge second derivative, that could drive up your error as well. Moreover, if f has a continuous fourth derivative, not just second, but fourth derivative on AB, then the error E in approximating the integral by Simpson's rule is, okay, catch this one. Okay, that b minus a, your interval here, raised to the 5th power. Now that can get some pretty significant error, but look at the denominator, 180 as opposed to 12, and n to the 4th as opposed to n squared. So that's going to be a pretty big denominator, so that's going to drive down the error. And then it's the maximum of that fourth derivative in that interval a to b. Okay, so there's the rules we'll use. Do I memorize these things? You better believe I don't. I don't trust my memory that much. Well, you could say, yeah, you're 69 years old, you shouldn't trust it. And we're absolutely right. But even when I was young and nearer my peak or prime or whatever you say, I never trusted my memory to remember exactly the numbers there. I always look them up. That's my rule. Okay, not Simpsons or trapezoid. Always look them up. Okay, in general, when using approximation, you can think of the error E as the difference between what you expect the true integral to be and the approximation. So theorem 8.6 that we just did states that the errors generated by the trapezoid rule and Simpson's rule have upper bounds dependent on the extreme values of the second derivative for trapezoid rule, the fourth derivative for Simpson's rule, on that interval a to b. Furthermore, those errors can be made arbitrarily small by increasing the n. Okay, remember, all it takes is increase that n, and look at what you're doing. The interval stays the same. That doesn't change. You can increase the n as much as you want to, especially if you're using a computer. Let it go, okay, and you can drive down that error, because when you take a bigger number, just punch it in your calculator. Do n equal 8, raise that to the 4th power. Oh my word, that is an enormous number. Multiply it by 180, an even bigger number. That's going to drive that error down big, big time. Okay. So that's usually what you do. Even if you have big second or fourth derivatives, all you have to do is do a bigger n, and you can wipe those out. Provided that second derivative and the fourth derivative are continuous, that is a requirement, and they're bounded. That means they don't go to infinity. Okay, so on that interval a to b. Okay, I think we're ready for example 3, and we got plenty of time for it. Let's do example 3. Determine a value of n, such that the trapezoid rule will approximate the value of integral from 0 to 1 of the square root of 1 plus x squared dx. Now, we're not really interested in what this is. We just want to know the value of n that will get you within an error less than 0.01. Now, I said before, usually 3 significant digits is good. They're only requiring 2 here. So this n's probably not going to be too bad. Now, do we have to use the trapezoid rule? No, I believe a trig substitution would probably work for this problem. But that's beside the point. What we want to do is see what the error is. Now, if you remember the formula from before, and you don't have to remember it, like I said, the absolute value of E, I don't memorize these things, you need to be less than or equal to, and remember what the thing was for trapezoid rule? B minus A cubed, okay? And here your B minus A is 1. So it's 1 cubed over 12n squared. And that's what you're looking for. Determine the value for n. So that's going to be what we're going to be looking for. Okay? Oops. That's multiplied by the maximum of the second derivative, absolute value of the second derivative. So that's multiplied by the maximum value of absolute value f double prime. Okay. I think that's how they wrote it, isn't it? Oh, they put of x. Okay. I knew something was missing there. So we've got a couple of things to do. Number one, we need to take the first derivative of this and the second derivative of this. So your function here, f of x, is equal to, I'm going to write it this way, 1 plus x squared to the 1/2 power. That's the square root of 1 plus x squared. So f prime of x is equal to 1/2 of 1 plus x squared to the, taking the derivative, you drop that by 1, minus 1/2, and you do the chain rule times 2x. So I'm going to do the 2 here, which wipes out that 2, and put my x here. And that's a piece of garbage. Okay, now, second derivative, f double prime of x. Okay, well, there's an x there. This time we've got a product rule we have to deal with. Okay, so it's the first x times the derivative of the second. Well, the derivative of the second here is a minus 1/2, okay, times 1 plus x squared to the minus 3/2, okay, I guess I should have put a bracket there, okay, and then my parentheses here, times chain rule again, that would be a 2 again, which wipes out that 2, and another x, okay, chain rule here. So what does that come out being? Bottom line, a minus x squared times, well, let me write it this way, over the square root of 1 plus x squared to cubed, okay, 1 over that. That's to the 3/2 power. Okay, that's ugly, I realize that. Okay, now, who cares about the minus sign? We're looking for the absolute value of that thing. Now, the question is, what's the maximum value of that thing? Well, here's the good place to start. Let's start at the endpoints and see what they tell us. So we are going from 0 to 1. So let's plug in a 0 first. That's going to be 0, okay, because the x equals 0. Hey, no error on that side. So I'm betting that it's going to be at when x equals 1. We might need to try some values in between, but I think we'll find out it's going to be at x equals 1. So let's see what it is when x equals 1. Okay, that's going to be 1 squared is 1. So there's your numerator of 1. And your denominator is going to be the square root of, when x equals 1, this would be 1 plus 1 is 2, square root of 2 cubed. Okay, so that would be 2 root 2. Okay, now, can we guarantee that's the maximum? Nah, you probably need to look at it, but if you think about this, it's starting at 0, and then this is a continuous function, so it probably is moving up the whole way. Okay, so let's see if that's what the book said. 1 over 2 root 2. Actually, I must have done something wrong here. I had an x squared there that they don't have. How did I get that messed up? Oh, of course. I only did half of the product rule. Okay, I did the first times the root of the second. Sorry, folks. That was a lot of wasted effort. Here we go. Sorry about that. Let me get rid of this part. And we'll come back and revisit that again. That was ugly anyway. I only did half of the product rule. Y'all let me get away with that? What are you thinking? Okay, we did the first times the root of the second, which I should have left what I had there. That was a minus x squared over 1 plus x squared to the 3/2 power. I put it downstairs, so lost that one. Okay, but then we've got a plus the second times the root of the first. Well, derivative of x is x, okay? And the second here is a minus x okay. I need to remember what that was x over 2, because I did the, no, okay. This x is not an x, it's a 1. That was when I took the derivative of 2x. I put the 2x up here. So that's minus 1/2 times 1 plus x squared to the minus 3/2. Okay, and this part we know is 0 when x equals 0. This part is not, though. This is minus 1/2, and when x equals 0, this is 1 to the 3/2 in the denominator. So that's a 1/2. The absolute value of that is 1/2. Okay? Now, they still get 1. Okay. How did I mess that up? Well, the old gray cells aren't working well today. There's too much going on. Let's take theirs as 1 because it's a bigger number. We could go back and plug in the x equal 1 and see what happens. They just tell us it is 1. So let's just take their word for it because I've taken too much class time today. Okay, so this is just going to be 1. Okay, so that doesn't contribute much of anything. So let's now figure out what we've got going on here. We're looking for n. So let's multiply both sides of the equation by n squared. And this gives us an n squared. And divide both sides of the equation by your e. Well, here's your e, 0.01. Okay, so this will be n squared is less than or equal to 1 over 12 times 0.01. Okay, we divided by that. Okay, now since we're dealing with absolute values and positive only, we're not going to mess around with the plus or minus here when we take a square root. So n is equal to the 1 over the square root of 0.12. I believe I did that right. I'm not going to trust anything I'm doing today because it's just, I feel really wacko. I got hit with a broadside today, so let's see what we got. Okay, I'm going to need it in scientific mode to get the square root 1 divided by 0.12 square root equal. I get 2.8. Let's round that to 3. You always, yeah, and that's what they got too. 2.89 they said. You round that to 3. Your n, you don't do a fractional n. You do n equal 3. So n equal 3 will give you the precision that you're looking for. Okay. Now they carry it on further, so I don't even know why they rounded that to 2.89. You round that to 3. Always round up. Okay. Don't ever, if you're doing the error calculation, you always err on the side of, on the conservative side. So you can choose n equal 3 because n must be greater than or equal to 2.89. So even though that had been 2.19, you'd have used 3. Okay. And apply the trapezoid rule, and they show what you get there. They didn't ask you to, but they did, and you got an estimate of 1.154. Okay, when you do integrate from 0 to 1 of that one. Now, that's your error estimate was where do they show you? Oh, your error estimate was they gave you in the problem 0.01. So if you subtract 0.01 from 1.154, you get 1.444. And if you add the 0.1 to that, you get 1.6164. Hey, why hang around with the 4 at all? You don't need it. Your error is only 2 digits. So I would have said 1.14 to 1.16. Okay. So you know your answers in between there. Now they didn't take it the next step and actually figure out what it was. I think you could have, like I said, I believe that's a trig substitution, but they're not doing it. We're running behind time on phone calls and everything else. Sorry about that. Let's just end it there. Okay, that finishes 8.6. Always do the concept check. I don't ever say it, but always say it, but please do the concept check. Make sure you understand the concepts. And then your homework exercise, excuse me, I've got the hiccups. Any of the odds 3 through 13, they're all at Calc Chat, 3's at Calc View. Any of the odds 15 through 23, they're all at Calc Chat. 17's at Calc View. Either 25 or 27, they're both at Calc Chat. 25's at Calc View. 29 or 31, they're both at Calc Chat. 29's at Calc View. Do 33, it's at Calc Chat. 35 or 37. Well, let's see. I'd say any of the odds 35 through, I think we have a whole bunch of them here. 35 to 47. Any of those, they're all at Calc Chat. I don't think any of those are at Calc View. All right. And that wraps up 8.6. Any questions on 8.6? Oh, let's see how they did this one. Sorry about that. I forgot this is one in the slide set. So let me erase my ink and see how they did it. By letting f of x equal to that, finding the second derivative, there's the first derivative, exactly like we found it. And then the second derivative, this is where I had an x out here, I think. Okay? And I haven't quite rationalized to myself how they got rid of the x, okay, in that second derivative. I guess if I thought about it long enough, I could get that, but they get that. In fact, I think I think you use both terms of that product rule here, and you will, something will cancel or divide away. And I think that's where it goes. Okay, so I just misdid my second derivative. Y'all would not make a mistake like that, would you? No, of course not. Okay, so there's your second derivative. Now, looking at it from that viewpoint, a 0 here is going to give you 1 as its error. A 1 here would be something considerably smaller than that. So sure enough, x equals 0 will be your maximum second derivative. Okay, the maximum value would be then at x equals 0, and that would be 1. Okay, so by the theorem we have the absolute value of the error, which we know from our given was 0.01, is b minus a cubed. Well, the b minus a is 1 minus 0, so that's 1 cubed is 1, and this will be 12 times n squared, and we're looking for n, and then this of course was 1, so this comes out 1 over 12n squared times 1. Okay, now we're looking for n given the e, so that would be, okay, 1 over 12n squared. We got it. Okay, they'll repeat the simplest things, leaving the complicated things undone, you know, but they want you to know that 1 over 12n squared times 1 is 1 over 12n squared. They wrote that one down, whereas back here they didn't show you how they went from here to here. That's a very complicated thing, but they'll write it down that 1 over 12n squared times 1 is 1 over 12n squared. All right, good. I'm glad you pointed that out to us. Okay, to obtain an error e that is less than or equal to that, you must choose an n such that, and basically what you do, oh, this is the error, 0.01. There, that is, they just written it this way, and they write that because of this, there's the less than or equal to that way. They flip sides here and flip them over this way too, and have 100 is less than or equal to 12n squared. Divide by 12, and then do take a square root. And that's how they got their 12 point. That is one of the most convoluted ways I can imagine doing that, but it certainly, every step was right. Okay, and that gave them that. So you always round up. That would be 3. So you can choose n equal 3 because n must be greater than or equal to the 2.89. Apply the trapezoid rule. Excuse me, I need that caffeine now, as shown in this figure, and it would be 1/6. Remember, that's how you start the trapezoid rule, because this was your B minus A over 2 2n, and n was 3, so that was 1/6. And then you plug in the 0 here, 1/3 here, 2/3 here, and 1 there. So the trapezoid rule was 1 times this plus 2 times that, with 1/3 in there, plus 2 times this with 2/3 in here, plus 1 times this with the 1 in there. Okay, and that's it's not an unreasonable calculation. This gives you a 1, and then you could do it with your calculator. It's pretty straightforward. It just has fractions. 1/6 times 1 plus 2 times 1 plus 1/9 plus 2 times 1, the square root, I should have said square root of 1/9. 1 plus 1/9. Square root of 1 plus 1/9 would be the square root of 10/9 plus 2 times the square root of, and this would be 1 plus 4/9. That would be 13/9, square root of 13/9, plus the square root of 2. And see what you get. Okay? Now, and that gave you approximately 1.154. Okay? Now, you know your error is less than or equal to 1.01, so when you subtract that from 0.01 from here, that means you're somewhere in between 1.044 and 1.144 and 1.164. If you subtract the 0.01 from this and add the 0.01 from this. And frankly, to me, it seems crazy to have those 4's at the end, because if your error is 0.01, why do you, to the nearest hundredth, why do you have a thousandths even out there? That just doesn't make any sense. Okay. Now, by adding and subtracting the error to this estimate, you know, yeah. Again, I wouldn't even write the 4's down here. 1.14 to 1.16. Okay. That is the last slide. We've already made the whatever you call them, the assignments. Let's close. I guess I'm going to have to move y'all because I can't close with you sitting there. So I'll move you up here. You can't see that, but I did. And now, see, we got about 18 minutes left. Let me make sure that Ashton isn't somewhere out there. No, he's not. Okay. So let's go to new share and 8.7. All right, now I've got to move everything again. Okay, and I'll probably have to do that to my whiteboard too. Let's just see. Yep. Well, let's see. I don't know yet. Yep, I'm gonna have to move it too. So let me get y'all back where you belong. Get this out of the way. And the whiteboard is where it belongs, so that's good. Okay, so let's go back to the PowerPoints. Okay, and we'll go from current slide. Okay, now when I opened this, it said not everything was coming through well, and that I think is why this mess is down here. We may hit another place in here, so there may be some corruption in this. It looks like there's a little bit of corruption in that too. But anyway, hopefully we'll be able to see most of the slide. We're still in Chapter 8, Integration Techniques and Improper Integrals. Let's move to 8.7. Integration by tables and other integration techniques. Okay, Now, if you hadn't already gathered from what we said last time, a lot of times, let me back off one moment. If I were writing this book, which I'm not, I would have put 8.7 where 8.6 was and then move 8.6 to 8.7. Because, frankly, everything we've done in Chapter 8 up before the last section, we were learning techniques to do. Okay? And guess what? Not all techniques will work with all integrals. So sometimes, if you can't figure out what technique to use, go to a table and see if you can find the integral in a table. And if you can, use it. But sometimes, this is why I would have put 8.6 at the end, not even a table will help. And if a table doesn't help, then go to a numerical method. So I would have reversed these order, because this is my next fallback. If I can't figure out how to integrate it, I go to the tables and see if I can. Okay, so that's what we're doing, integration by tables. And when it says or other integration techniques, techniques you use within the tables, to get it into the tabular form. So that's what we're going to do. Our objectives here are to find an indefinite integral using the table of integrals. We'll do a few of those. We'll find an indefinite integral using reduction formulas, which you can sometimes find in tables, okay? And then we'll find an indefinite integral involving rational functions of sines and cosine. You thought, haven't we already done that? Well, not the ratios, rational functions. We'll see. We have done some of those, but we'll expand that technique a little bit. So there is a new technique. So let's do integration by tables. Many people find tables of integrals to be a valuable supplement to the integration techniques discussed in this chapter. Do you want me to rephrase that sentence? Many people use tables of integrals rather than doing the techniques that we've learned in this thing, because those techniques are all there in the tables as well. So rather than trying to remember, okay, how do you do integration by parts or partial fractions or something like that? Now, some of those, they won't have everything in there, but sometimes they will, okay? So a lot of people just go straight to the integration tables, okay, without even trying different technique. Now, if you see something and you know, oh yeah, I can integrate that, do it. It's quicker than doing the table. Here's another phone call. Let me see. Sorry about this, folks. Let me pause this recording around noon, so I'll be out of class by then. Boy, what a day it is. Okay, not one thing, another. So anyway, integration by tables. Okay, and here they go a little bit further. Many people find tables to be a valuable supplement. Blah blah blah. Tables of common integrals are found in Appendix B at the end of the book. Now this is a limited table, okay? When I was in, I think it was physics in college, one of the first physics instructors not one of the first, but one that I had, he got a really good deal on, and this, I don't even know if they're in print anymore. It was called the CRC, Chemical Rubber Company, put out a table, and they had volumes of these things, but one of them was a mathematical volume, and boy, in that, I have never seen thinner paper in my life, and the book was about that thick. So you can imagine they had everything mathematical in there. Now this was before the days of calculators. This is before the days really of computers. Everybody had to look up everything in a table to get the values, because it took forever to do them by hand. So I have a CRC. It's on the Bessemer campus in my office, a CRC table, and boy, does it ever have any. If you look in the back of the book, it may be 100 common integrals they have in that one. I would say the CRC table probably was in the thousands. Okay, so it has at least 10 times as many as what you have in the back of the book. So you can find all kinds of tables of integrals. Don't think you're limited to that little one in the appendix in the back of the book. So integration by tables is not a cure-all for the difficulties that can accompany integration. Using tables of integrals requires considerable thought and insight and often involves substitution. So that's the additional techniques we'll be looking at. Each integration formula in Appendix B can be developed using one of the more of the techniques to verify several of the formulas. So like I said, even in Appendix B, you're using the techniques we've already used in 8.1 to 8.5. Okay, so a lot of people don't even try to remember the techniques, they go straight to the tables. Okay, now I can't get this to advance. Okay, now let me see if I can find where they picked up this example 4. Formula 4. Okay, that's they skipped the little thing they did in the top half of page 566. Do you want me to go through that one with you? It's fairly easy to do. I'll be glad to do that. Well, actually, they're just showing you a how you use your techniques that we've already done. Okay. I don't know why they left them off the slide set, but the integral of x log x, that's a integration by parts. Okay. Integral of log x over x, that's a power rule, believe it or not. Okay. Integration of 1 over x log x, that's the log rule. Okay. But the integral of x over log x, not an elementary function, so not even you will find that in a table. Okay, so that's what those at the top half of page 566 are dealing with. Okay, now then is where this stuff came in. Okay, many people find blah blah blah, each integration formula in a problem be blah blah blah. Okay, so now we're down to the bottom half of page 566, and that's where we pick up here. And this is for instance, what if this was your integration? Okay, the integral of u over a plus bu squared. Okay, if you go to the table, okay, back of the book, and it's not exactly in the back of the book. I don't know if how many of you have books, if you have to use ebooks. I don't know what you're using now, but in the very back of the book there's a bunch of pages that are completely blank. I don't know why they put those in there, but then you have your index at the back. You have to go, so it's not at the back of the very back of the book. You have to thumb through all the index. Then you have the answers to your odd number exercises. That's a huge portion in the back of your book. Okay, so you have to thumb through all those. Okay, finally you get through all the answers to the odd number exercises somewhere here, and those are and the way they number appendices, they say this is, they start numbering over again, and that began on page A23. Why don't they just continue numbering? Because I don't know where A23 is. You have to really look. Okay, so before that you have appendix C, and that appendix C is, let me find it, it's a pre-calculus review. Okay, Cartesian plane. Okay, that's C2, Cartesian plane. Okay, go on back before that, and you get C1. C1 is pre-calculus review, and that was real numbers in the real number line. So you have all that in Appendix C. Okay? And again, they're numbering these. So finally you get to Appendix B. Now what do? I put a piece of paper in there, okay? So I don't have to thumb through all that in the back, okay? And they said Formula 4. Now Appendix B has a whole bunch of pages too, not as many as Appendix C did. It only has a few pages. There is an Appendix A, and that's proofs of selected theorems. Not going to do that, okay? That's just one page. Appendix B starts on A3, okay? I also want to have a piece of paper marking where we are in the book. And here we have Formula 4, okay? And that's the one that they give here, the integral of u over a plus bu squared du, and they tell you what it is. 1 over b squared times a plus over a plus bu plus the log of absolute value a plus bu plus c. Okay? Now, how do you do that? How can you verify that? Method of partial fractions. Okay? Because this was, you would do an since this is a quadratic down here, okay, that would be, well, you can go back and review partial fractions. We don't have a lot of time, 4 minutes left, so I can't go back and redo the whole thing. But this is a shortcut from having to do method of partial fractions, okay? And then for some reason they jump to the next page in Appendix B, and Formula 19, okay, is the integral of a plus bu over u, the square root of a plus bu over u du, and that one almost certainly is going to be a trig substitution. No, integration by parts. I'm sorry, integration by parts. And you have one function up here and another function down here integrated by parts. Okay, now Formula 84, which is another page over, and that's this one, 1 over 1 plus EU du, and that's just a substitution problem. So all these are using, everything in Appendix B is using one of the techniques we've already studied. Okay, it's just perhaps a shortcut for you. Rather than going back and trial and error figuring out which technique to use, just use the table. Okay, but some of them are so simple, rather than going to the table, it's easier to just go on and do the technique you know. Okay, it says, note that the integrals in Appendix B are classified according to the form of the integrand. Okay, so let's go back to the very first of the thing. The very first says forms involving u to the n. If you have to go to the table to do that, you need to go back and review, okay, integration. That is just too simple, okay? But they can come up with some that are a little more complicated, but in case you forget, go to it, use it. Forms involving a plus bu. Now, they can come up with all sorts of ways to complicate that, so this is using, perhaps the table is useful there. Then, forms involving a quadratic form, okay? That is, okay, forms involving u to the n would be formulas 1 and 2. Involving a plus bu, that's formulas 3 through 13, okay? Involving your quadratic, that is 14 and 15. Involving the square root of a plus bu, so this is a plus bu to a whole power, this is a plus bu to a fractional power. That one, you use those in 16 through 22, okay? a squared plus or minus u squared, that, sounds like a trig substitution to me, but that would be 23 to 25. The square root of u squared plus or minus a squared, another trig substitution, that would be 26 through 36. Okay? Square root of a squared minus u squared, another trig substitution, that would be 37 to 45. Okay? And then your trigonometric functions, okay, that would be your sines and cosines are 46 to 58. Tangent, cotangent, secant, and cosecant are 59 through 74. Okay? Your inverse trigonometric functions, they would be 75 to 80. So that's one reason I don't even try to remember those. I'll always look those up. Exponential functions, 81 to 86. Logarithmic functions, 87 through 91. Now what they don't mention here are the hyperbolic functions. And I don't usually mention them either because they're so much easier to do, I think, as exponential functions. Because the hyperbolic functions are just made up functions that express certain exponential functions. So they're easier to do as exponential than having to go through hyperbolic. Okay. So here's example 1. So let's go back to the front to where we were in the class. Oh, we've just gone over 1 minute. Sorry that we didn't have a full class today. With all the things going on, this has been a crazy day. So we'll begin next time with on page 567, example 1. Now here's my question to you. This is the last class we have before Thanksgiving week, because next week there are no classes. Y'all did know that, didn't you? Okay. All right. Do you want me to go on and put the chapter 8 test out there because we're not through with it. We've still got the table things to do, and I'm done. I think I decided we would not do improper integrals. So you want me to go on and put the chapter 8 test out there so you'll have the Thanksgiving week to work on it, since you're probably not doing too much on Thanksgiving because of COVID and stuff. You want it there or not? Okay, all right. I'll try to get that done. If I didn't have to go back for blood work again today, I'd say this afternoon. I don't know when I'll get it done. I don't think the transfusion will take long on Friday. It may be Friday before I get it done, but I'll try to get it done before Thanksgiving holidays. But if not, I'll probably have time Monday, Tuesday, and Wednesday of next week to do it. So I can't promise you anything, but I'll try to get it done before we see you again. Okay, so good deal. Any questions? All right, good deal. I'm going to stop sharing now. I'm sick and tired of sharing. And let me go on and end the recording if y'all don't have any questions. So take care. Be safe. Hey, family's important, but health is also important, and the health of your family is important. So don't overdo anything this weekend or this coming week. If possible, stay as isolated as possible. I know it's terrible to do on Thanksgiving, but try to be careful. Be very careful. Okay? Take care. We'll see you after Thanksgiving. Bye-bye.